Now, in the second half of this lecture, we will study dimension of subspaces in a finite dimensional vector space. K vector space V. So, let us write in a form of theorem. Let V be a finite dimensional vector space K vector space and W be a subspace of V, K subspace of V. Then 1 W is also finite dimensional. And the dimension of W cannot be more than dimension of V. This is clear because if finite, you remember in earlier part we have noted that if you want to check somebody is finite dimensional and dimension is less equal to n, then we need to check that every n plus 1 vectors are linearly independent or linearly dependent. So, if you have n vectors, if you call this dimension of V as n, if you take n plus 1 vectors in W, then they are also vectors in V, and because dimension of V itself is n, they will be linearly dependent. So, whether they are in V or W, linear dependency does not matter. Okay. So, second, every basis of W can be extended to a basis of V. This is also direct consequence of the exchange lemma, exchange theorem, because you pick up a basis of W, because it is a basis of W, they are linearly independent, and we can add some more elements in this to get a basis of V. This was precisely the content of the exchange theorem. Third one, if you want to check V equal to W equal to the full space V, so W equal to V if and only if the dimensions are equal. This is again follows from the fact that if you have correct number of vectors, you to check that they are linearly independent or basis or generating system, that is the same equivalent. So, this is also clear. So, proof I will just say easy to verify. Now, I come to a very important formula which we will use many times in future, that also this also shows us how one can work with basis. So, this is usually called a dimension formula. It connects the dimension of a intersection of two subspaces, dimension of sum of two subspaces, and the dimensions of them. So, let us write it very precisely. Let U and W be two subspaces of a vector space K vector space V, we do not need to assume V is finite dimensional, we only need to assume that U and W are finite dimensional. Suppose that U and W are finite dimensional. Then U intersection W and U plus W are also finite dimensional. And dimension of U intersection W plus dimension of U plus W equal to dimension U plus dimension W. Nice formula. This is called dimension formula. Later on I will show you how it is used for many proofs. Okay. So, let us try to prove this. So, first of all, so proof. Note that this intersection U intersection W is a subspace of U also subspace of W, and U is finite dimensional given, and we have just checked above that finite the subspace of a finite dimension is also finite dimensional. So, that proves that. So, first that proves that U intersection W is also finite dimensional. Since U is so. Now, to prove that U plus W is finite dimensional, and this formula we will do it together. I just want to recall you a definition of U plus W. U, remember, recall that U plus W is the smallest subspace of V which contain both U and W. This is the definition of U plus W, and immediately after definition one can check that U plus W is precisely the sums U plus W, where U varies in U and W varies in W. So, to check this, if we remember, what we need to check is the right hand side is a subspace and it contains both U and W, and it is the smallest one. So, this is very useful to. Okay. So, now let us try to prove this formula, and together with this is finite dimensional. Okay. So, first what we do is choose, we know every vector space has a basis. So, choose a basis x1 to xr of U intersection W. This is a subspace of U, also subspace of W. Now, this is a basis of this subspace of U. So, I will extend these two bases of U by adding few vectors in that. So, x1 to xr along with u1 to us basis of U. This I can do it by again by exchange theorem. Similarly, I do it for W also, x1 to xr, W1 to WT basis of W. Now, I put all of them together. Now, we claim that all together x1 to xr, u1 to us, w1 to wt form a basis of u plus w. For that we need to check that they generate u plus w and they are linearly independent. So, first let us check linear independence. First let us check that these vectors x1 to xr, u1 to us, w1 to wt are linearly independent over K. So, suppose there is this linear relation. Suppose that A1 x1 dot AR xr B1 U1 plus BS US plus C1 W1 plus CT WT, this combination is 0 where A1 to AR, B1 to BS, C1 to CT are scalars. And now our job is to prove that all A's, all B's and all C's are 0. So, first I want to shift this to the other side. So, that is A1 x1 plus AR xr plus B1 U1 plus BS US equal to minus C1 W1 plus CT WT. Now, left hand side belongs to all these x1 to xr, u1 to us, it is a basis of u. So, it belongs to u. The right hand side belongs to w and they are equal. So, that means they belong to u intersection w. That means I can write this as a linear combination of x1 to xr.
Font is getting small.
Oh, the letters.
Yeah.
Okay. Okay, I will try bigger. Okay. This means the left hand side I can write as a linear combination of x1 to xr. So, that means I would write this as a1 prime x1 plus AR prime xr for some other constants a1 prime AR prime in K. But then this equal to these w's, but I know the x1 to xr and w1 to wt is the basis. So, they cannot have linear relation among them unless all coefficients are 0. So, that implies C1 equal to CT equal to 0, since x1 xr w1 wt are linearly independent. Over K. So, we have proved C's are 0. Now, put back this in the given linear equation. No. Therefore, we get A1 x1 plus AR xr plus B1 U1 plus BS US. This is 0 because we already proved C's are 0. Now, but now x1 to xr and u1 to s are linearly independent by our choice, because that form a basis of u. So, that shows all the coefficients must be 0. So, A1 to AR are 0 and similarly B1 to BS are 0. So, altogether we have proved that all A's are 0, B's are 0 and C's are also 0. So, that proved linear independence of x1 to xr, u1 to us and w1 to wt. Now, we want to check that this is a generating system. So, we want to check that x1 to xr, u1 to us, w1 to wt is a generating system for u plus w. That means we want to check that if a subspace contain all these guys, then it contains u and w also. But you know u is by our choice, u is generated by x1 to xr along with u1 to us, and w is generated by x1 to xr and w1 to wt. So, if some subspace contain all these guys, then it contains u and it contains w also. So, therefore, it will contain u plus w also by definition. So, that checks that u plus w is generated by x1 to xr, u1 to us and w1 to wt. So, we have proved that u plus w is generated by these guys, they are linearly independent, so it is a basis. So, dimension of u plus w is r plus s plus t, and dimension of u intersection w was r, because it has a basis which has r elements. And what do you want to prove? We wanted to prove that sum of their dimension equal to, so the sum, if I add here, I have to add here. So, the sum is therefore r plus s or r plus s plus r plus t, but dimension of u is r plus s and dimension of w is r plus t, because u has a basis x1 to xr, u1 to s, and w has a basis x1 to xr, w1 to wt. So, that proves this formula also. So, it proves both together, u plus w is finite dimensional of dimension r plus s plus t, and the dimension formula holds. So, this completes the proof. Okay. Let us, I want to discuss still some more examples. Okay. We discuss some examples. So, example 1. Suppose V is one dimensional vector space, V be one dimensional K vector space. That means V has a basis consisting of one element. So, this means, so that is V is Kx, where x is any non-zero vector. Once it is a non-zero vector, it has to generate a non-zero subspace, and only we know subspaces will have smaller dimension. So, the dimension of a subspace can either be 0 or 1. So, in this case dimension 0 means the 0 vector 0 subspace, and V, they are the only subspaces. Now, let us take a little bit bigger case. So, assume dimension V is 2. So, if dimension V is 2, then what are the possibilities for dimension of a subspace? So, then the subspaces can have dimension the 0 or 1 or 2. If it is a 2 dimensional subspace, then the only 2 dimensional subspace is V, because we have noted if somebody is a subspace of dimension equal dimension to ambient vector space, then it has to be equal to that. 1 dimensional subspaces are precisely generated by 1, it has a basis consisting of 1 element. So, it is of the form Kx, where x is a non-zero vector, and 0 dimension is the 0 vector space, 0 subspace. So, these are the only possibility. Now, this I want to generalize further to arbitrary dimension. So, for example, just to get a feeling, if dimension is 3, then what are the possibilities for this dimensions of the subspaces? Either 0 or 1 or 2 or 3. The dimension 3 we know it has to be the whole V. Dimension 0 also we know it is the 0 subspace. Dimension 1, it is generated by 1, it has a basis consisting of 1 element. So, it is a basis, it is like this Kx x non-zero. Dimension 2 case, it will have a basis consisting of 2 elements. So, if xy is the basis of that, then it is of the form Kx plus Ky, where now xy are vectors and not arbitrary vectors, they are now linearly independent. So, you choose a pair of vectors which are linearly independent, and that will give you a 2 dimensional subspace. And how do you check 2 vectors are linearly independent or not? Just check that y, for example, cannot be in the subspace generated by x, then it has to be linearly independent. So, this is the way one checks a 2 dimensional vector space. Okay, also the usual language which I will use later, that if it is 1 dimensional subspace, one usually calls it a line. 2 dimensional subspaces are called planes, and so on. 3 dimensional subspaces will be called threefolds, and so on. That will be the language which we will use later on in a geometric situation. Okay, I want to generalize this to arbitrary. So, that is let us write it with another example. So, these are also called flags. So, let V be a K vector space of dimension n with basis V1 to Vn, and let us look at the subspaces. Then the subspaces Vi is a subspace of V generated by V1, V2 etc. up to Vi. And I is running from 0 to 0, 1 up to n. Note, when I is 0, that means this is a 0 vector, this is 0 subspace. So, V0 is 0, V1 is k V1, V2 is k V1 plus k V2 and so on. Vn minus 1, Vn is the whole V because V1 to Vn is a basis, and at each stage this inclusion is proper. Because these V1 to Vn are linearly independent. So, Vi cannot belong to the earlier subspace generated by the earlier case, because otherwise V1 will get a linear dependence relation between V1, V2 etc. Vi. So, this is a proper. This is a chain of, so this is a chain of subspaces, and at each stage dimension of Vi is precisely I. This is a ascending chain. At each stage subspace will have dimension I. At each I the subspace has dimension I, and this is a maximal chain. Moreover, it is a chain of maximal length. This is a chain of length n, and we cannot insert anywhere any other subspace so that it becomes longer than n. Just because if you insert, then what will be the inserted subspace dimension? You see, it should be bigger equal to I, and it should also be smaller equal to I plus 1. So, there is no possibility. So, this is such a thing is called a flag. Okay. So, such a maximal chain of subspaces of V is called a flag in V. So, some more examples. So, let us also look at next one. Suppose U and W are two subspaces of V, and suppose U and V both are finite dimensional. Then we know from the dimension formula it follows that the dimension of the sum is bounded by the sum of the dimensions. Because what we proved is this plus dimension of the intersection equal to this equality. So, in any case, and I am now concerned when will this equality hold. So, this equality moreover equality holds if and only if the intersection should be 0 subspace, because 0 subspace will have dimension 0 and then there will be equality. In this case, we say that the sum U plus W is a direct sum of u and w. We will use this concept more in the later lectures. So, I think I will stop and we will continue in the next lecture. Thank you.